Little minds, welcome to All 4 E-Learning program. This is physics session number 46, right? Now in this one, we will take up the applications of the electric potential due to a dipole. The applications of it. So how does a dipole behave, right? For various things, and we'll take some problems also. Now before that, let us have a general formula for the electric potential due to a dipole at any arbitrary point. At any general point in its vicinity, then the potential due to this at any point. Let's derive the formula for that, then apply the things for any for any case, right? Let us consider an electric dipole. Look, consider an electric dipole with minus q and plus q charge, right? So electric dipole is a combination. We know electric dipole is a combination of two equal and opposite charges. Two equal and opposite charges, well separated by a distance. This distance is A, right? This is A like this, and even this is also A. The total length of the dipole is 2A. So dipole moment P is 2AQ. First point. Dipole is a combination of two equal and opposite charges separated by a distance. The dipole moment is the product of either of the charge and the length of the dipole. Either of the charge is q, length of the dipole is 2. Is it? So this is the center. All distances are to be measured from the center there. Is it? Now we have to find out the electric potential due to this dipole at any arbitrary point. What are the various things which are required? We know electric potential due to a point charge. Potential is the electric state of the body. It is defined as the amount of work done per unit charge. Work done per charge. V is W by Q. The electric potential due to a point charge is 1 by 4 pi epsilon naught Q by R. The potential at any point. And the resultant potential is the algebraic sum of, potential due to many charges, multiple charges. It is the algebraic sum of all the individual potentials, right? Taking them individually. And potential is a scalar. For a positive charge, it is plus. It is negative charge, it is minus. So you have to substitute the respective potentials to find the resultant potential, right? Now, so with respect to this dipole there, now I have to find the potential due to this at some arbitrary point P. So let P be an arbitrary point P from the center of the dipole, which is at a distance R. This is the distance R. R is the distance. And the line joining that point P, the line makes an angle theta with the axial line of the line joining makes an angle theta with the axial line of the dipole. This is the axial line of the dipole, right? Now next what you have to do, so to find the potential, how to find the potential due to this? It is a combination of two discrete charges. So the total potential is the algebraic sum of each. So you have to find the potential due to each charge, then add algebraically. So to find the potential due to each charge, 1 by 4 naught, the formula is 1 by 4 naught Q by R, charge into distance. So first I have to find the potential due to positive charge, then the potential due to negative charge, add. To find the potential due to positive charge, first I should know the charge and the distance. Well, the charge is plus q. The distance of the point, this is the distance. Let this distance be r1. Well, we don't know r1, but we know r. What we shall do is, we shall drop a perpendicular onto this. Perpendicular from here to here. This is a right angled triangle. Now, from this right angled triangle, let's suppose we'll name them. Let this be A, let this be B, and this point is C. Similarly, extend this, drop a perpendicular from it. This is D. Here also this is a perpendicular. Is it? If this is angle theta, even this is also theta, because vertically opposite angle theta. Now, from this diagram, the distance from B to P is almost same as the distance from C to P. Like for example, there are two points like this. If I drop a perpendicular, this length and this length will be almost same, right? So therefore, so the distance from this charge, that is BP, is same as CP. So BP is equal to CP. But what is Cp? It is OP minus OC. So it is OP minus OC. OP minus OC. Right? But what is OC? Now from this right angle triangle, you take cos theta. From this right angle triangle, cos theta. Theta is this. The cos theta is adjacent side by hypotenuse. Adjacent side is OC. So adjacent OC by hypotenuse. This is hypotenuse OB. So cross multiplying, OC is OB cos theta. But OB is nothing but A. So OC is A cos theta. So therefore BP is nothing but R1. So R1 is equal to, this is CP. CP is OP minus OC. So OP is R minus OC. It is A cos theta. This is equation 1. Similarly, now consider, let the distance of the point P from A, from the negative charge, let this distance be R2. This is R2. Well, again, if I drop a perpendicular, extend this and drop a perpendicular. Now, AP R2 is same as DP, like this. So, AP is equal to DP. But what is DP? It is OP plus OD. So, OP plus OD. Well, OP I know, O to P is R, but OD I have to find. Again from this right angle triangle, take cos theta. Cos theta adjacent by hypotenuse, that is OD by OA. So cross multiplying, OD is OA cos theta. Well, OA is A. So therefore AP is R2. R2 is DP. This one. So this is equal to OP. OP is small r plus OD. OD is OD. This is A cos theta. So this is equation. This is equation 1 and this is equation 2. So this is the important part of the derivation, where the distances of the point P from the respective charges you have to find. We don't know the distance. We are not given with the distance directly. We are given with the distance from the center of the dipole. But we have to find the distance from the respective distance from the charges. So this distance is R1. How do you get R1? Drop a perpendicular. So this is equal to this. Right? And this is a right angle triangle. Then cos theta. So this total distance is R1, but I want only CP. So this CP is R minus OC. Well, OC I have found it as A cos theta. So R minus A cos theta. Similarly, distance from this charge, right? Extend OP and drop a perpendicular like this. Then the distance AP R2. AP is R2. The distance AP is equal to DP. So AP is DP. But what is DP? Total distance? It is OP plus OD. OP plus OD. OP is R and OD is, we have found it as A cos theta. So R plus A cos theta. So first find the respective distances. The respective distances are R1 is this and R2. Well, the distance R2, this distance R2. R2 is equal to R plus A cos theta. Okay. Now next we have to find the potential due to each charge. Now let me take up the potential due to positive charge. If I take the potential due to positive charge. Potential due to positive charge plus Q at P is, let it be Vp. Well, we know the formula for the potential due to point charge. Potential due to point charge is 1 by 4 epsilon Q by R. So it is 1 by 4 pi epsilon naught. Charge is plus Q by the distance of the point from the positive charge, R1. So Vp is equal to 1 by 4 pi epsilon naught plus Q by R1 is R minus A cos theta. So it is R minus A cos theta. Similarly, the potential due to negative charge. at P. The potential due to minus Q at P, I want to find the potential due to this charge at point P. And let this potential be Vn. It's 1 by 4 pi epsilon naught. Now the potential due to the negative charge, it is minus Q by the distance of that point from this, it is R2. So substituting potential due to N, it's 1 by 4 pi epsilon naught minus Q by R2 is R plus E cos theta. So this is equation 3, this is equation 4. Now the resultant potential of the dipole at P, let this be VR. So VR is equal to potential due to P, potential due to positive charge plus potential due to negative charge, Vp plus Vn. So the resultant potential is potential due to positive charge, it's 1 by 4 pi epsilon naught plus Q by, it is R minus A cos theta, plus 1 by 4 pi epsilon naught minus Q by R plus A cos theta. Now take the things, common things out. So it's 1 by 4 pi epsilon naught even, so it's plus Q by R minus A cos theta plus into minus Q by R minus A cos theta. Take even Q also common out. So it's Q by 4 pi epsilon naught. In the denominator, this is R minus A cos theta. Sorry, this is R minus and this is R plus. So this is R minus A cos theta and this is R plus A cos theta. So the LCM of this is R square minus A cos theta whole square. A plus B into A minus B, R square minus A cos theta whole square. Well, this comes here and this comes here. R plus A cos theta minus of R minus A cos theta. R plus A cos theta minus of R minus A cos theta. So the resultant potential is Q by 4 pi epsilon naught. The denominator is R square minus A square cos square theta. And here if I simplify, it's R plus A cos theta minus R plus A cos theta. Plus or minus or cancel. Then I'll get it as, so the resultant potential VR is equal to Q by 4 pi epsilon naught. This is A cos theta plus A cos theta. It's 2A cos theta by R square minus A square cos square theta. But we know 2AQ. I have already stated 2AQ is the dipole moment of the dipole. So I can substitute this 2AQ as the dipole moment. So it's P, dipole moment P cos theta by 4 pi epsilon naught R square minus A square cos square theta. So the resultant potential at any point is 1 by 4 pi epsilon naught P cos theta by, it is R square minus A square cos square theta. This way you find the resultant potential at any arbitrary point, in the field of the dipole, any general point. The potential at any general point due to a dipole is 1 by 4 pi epsilon naught P cos theta by R square minus A square cos square theta. Right? So this is the formula where P is the electric dipole moment of the dipole, cos theta. Theta is the angle made by the radius vector with the axial end. The distance, this radius vector with the axial end, this is theta. And R is the distance of the point PR, and this is A cos theta. A is half the length of the dipole and theta is the angle made by the radius vector of the dipole. So that is the formula for the electric potential due to an electric dipole at any arbitrary point, any general point. 1 by 4 pi epsilon naught P cos theta by R square minus A square cos square theta. Right? So this way you find the potential. So first what did I do? Consider an electric dipole, minus Q plus Q. Length is 2A. So dipole moment is 2AQ. Take an arbitrary point P. arbitrary point P at a distance r from the center of the dipole. All distance are measured from the center of the dipole. So r distance is r. So the distance r is the distance from the center of the dipole, but I want the distance from respective distance from either of the charges. So for which what I do, I shall make some small construction, right? So let the distance from the positive charge be r1. Let the distance from the negative charge be r2. Now drop a perpendicular here. So this r1 distance BP is same as CP. But what is CP? OP minus OC. Right? OP is r. First find OC. How do you find OC? From this right angle triangle cos theta adjacent by hypotenuse. So I get A cos theta. So therefore R1 is nothing but CP, which is R minus of A cos theta. So BP is CP. CP is OP minus OC. OC is A cos theta. So this is A cos theta. And even this is also A cos theta. So therefore R minus A cos theta. Similarly, let the distance of the point be from AB R2. Then extend this double perpendicular. Now DP is AP. So AP is equal to DP, the total distance. But what is DP? OP plus OD. OP is R, OD is again A cos theta. So R plus A cos theta. So respective distances. Then potential due to positive charge plus Q by distance R1. R1 is R plus R minus A cos theta. Potential due to negative charge plus minus Q by R2. R2 is A plus R plus A cos theta. Total potential is potential to positive and negative. Add both. Right? So for positive it is plus potential, for negative it is minus potential. The sum. So you get it as Q by R minus A cos theta minus of Q by R plus A cos theta. Take Q common. So LCM R square minus A square cos square theta. R plus A cos theta minus R minus A cos theta. So total, the final answer, you simplify, apply mathematics, simple algebra. So you get the potential, resultant potential at any point. The resultant potential P is P cos theta by this. So potential at any arbitrary point is directly proportional to P cos theta. P is the dipole moment of the dipole. It is directly proportional to cos of the angle made by the point P, the radius vector with the axial line, and it is inversely proportional to 1 by r square minus a square cos square theta. Right? So this way we find the potential. Now from this you can evaluate from this general point, from the potential due to potential due to a dipole at any arbitrary point, you can make out the potential on the axial line, equatorial line, any point. You can define the potentials at any point like this. So for a dipole, suppose this is a dipole, minus Q plus Q, right? For an electric dipole, minus Q plus Q. This is the axial line, this is the equatorial line, and this is the arbitrary point P making an angle theta, right? The electric dipole moment of this is P. Distance of the point is R. Then. So at any arbitrary point P, potential at any point P, 1 by 4 pi epsilon naught. The dipole moment is P. Angle made by it is P cos theta by R square minus A square cos square theta. Well, now this is for any dipole. Suppose if it is a short dipole. For a short dipole, right? For a short dipole, in a sense, the length of the dipole is negligible when compared to distance to the point. So that is A is less than R. A less than R. Then under such conditions, then the potential at any resultant point P, it's 1 by 4 pi epsilon naught P cos theta by, this is negligible and this is square of the things, both are less than 1 values, negligible. So I get R square. So from this, for a short dipole, V directly proportional to P, V proportional to cos theta, and V proportional to 1 by R square. For a short dipole, potential inversely proportional to square of the distance of the point. Now, suppose had this point lie on the axial line, had it been on the axial line, if P is on the axial line, In a sense, if P is on the axial line, the line OP will make an angle 0 with the axial line. So theta will be 0. So if I substitute 0, Vp is equal to 1 by 4 pi epsilon naught P cos 0 by R square minus A square cos 0 square. Well, cos 0 is 1, this is 1. So we get it as P into 1 P by R square minus A square. This is the formula what we have proved for the axial line earlier, right? So for a short dipole, continuing, if it is for a short dipole on the axial line, it's 1 by 4 pi epsilon naught. A is negligible, so simply P by R square. If the same point lies on the equatorial line, the same point is on the equatorial line, in the sense, right, if P is on the equatorial line, in the sense theta is 90, then if it is theta 90, then substitute 90 here. So potential on the equatorial line, this is axial line, this is equatorial line. So it's 1 by 4 pi epsilon naught P cos 90 by R square minus A square cos 90 square. Cos square 90. But you know cos 90 is 0. So the final answer is C. So on the equatorial line, whether it is short dipole or any dipole, the potential is 0. Right? So generally the general formula for the potential at any arbitrary point, it is P cos theta by R square minus A square cos square theta. Then for a short dipole it is like this. On the equatorial line it is 0. On the axial line it is like this. For short dipole A is negligible. A is not considered. So therefore potential due to a dipole at any arbitrary point, the general formula axial line, equatorial line. For a short dipole, for where A is very much less, these are the formulas, and that is the application there. So now on this, suppose he is going to ask you some questions like this. Now suppose there is a dipole minus q plus q, right? Consider any 2 points, one on the axial line, one on the equatorial line, which are equidistant from the dipole. Let's suppose this is R and this is also R. Then he is asking to find the potential difference between the point on the axial line and point on the equatorial line E. What is the potential difference between A and E? Potential difference between A, potential on the axial line and potential on the equatorial line, right? So this is the electric potential at A minus potential at E there. Now potential on the axial line, it's 1 by 4 pi epsilon naught P by, if the distance of the point is R and we are considering it as a short dipole, so it is P by R square. On the equatorial line, we know the potential is 0. So therefore the potential difference between any 2 points, potential difference between 2 points, point on the axial line, and a point on equatorial line. This is 1 by 4 pi epsilon naught P by R square, because potential at any point on the equatorial line it is 0. So potential difference between these two is like this. So electric potential due to potential or potential difference between these two is termed like this. Similarly, suppose, imagine, this is a previous entrance question, a small electric dipole at the origin. Small electric dipole is at the origin. There are 4 points on the circle whose center is at the origin. There are 4 points like this whose center is at the origin like this. So A, B, C, D like this. The dipole is at the origin. The center of the dipole is at the origin. You know, this is the electric symbol for dipole. I was telling you, a dark arrow represents the symbol for a dipole there, short dipole. So a short dipole is at the origin like this, is at the origin. Its dipole moment is P. Dipole moment is P. Then he is asking to find the potential difference between potential at various points. Suppose if the dipole is A, this point is A comma 0, this point is 0 comma A, this is minus A comma 0, and this is 0 comma minus A. He is asking you to find the potential difference between various points. Suppose if he is asking you to find the potential difference between B and D, BD, well, B and D lie on the equatorial line of it. At all the points on the equatorial line, potential difference is 0. So potential difference between B and D is 0. This is potential at B 0, potential at D 0, it is totally 0. Suppose what is the potential difference between A and B? A is on the axial line, B is on the equatorial line. But this is potential at A minus potential at B. This is 0. So therefore potential at A 1 by 4 pi epsilon naught, dipole moment is P, and the distance, the radius of the circle is A. So this is A square. Similarly, the potential difference between B and C, well, potential at B 0, potential at C, it is like this. Potential at B 0 minus of 1 by 4 pi epsilon naught. You know, onto this side it is near to negative charge, so you will get negative. So it's minus P by A square. Well, minus or minus becomes plus. So you will get again 1 by 4 pi epsilon P by A square. Similarly, potential difference between CD, AD like this. So suppose if he is asking you to find the potential difference between A and C. Well, this is a important question. So I was telling you, if I take the point here, which is nearer to positive, the potential is positive. You know, you just see the things. Onto right side of the dipole, onto this of the dipole, there is positive charge very nearer to the points. At all the points onto right side of the dipole, all the points are nearer to the positive charge of the dipole. You know, positive charge of the dipole is here, negative charge of the dipole is here, the direction is here. So, with respect to y-axis, all the points on the right side, that is first quadrant and fourth quadrants, they are all nearer to positive charge. Then the positive potential is more, they are far away from the negative charge, negative potential is less. So the potential is, positive potential is dominant. So positive potential is dominant in the sense the potential is positive. Similarly, if I take all the points on the left side of the dipole, here, these two, second and third quadrant, these are all nearer to the negative charge, far away from the positive charge. Nearer to the negative charge in the sense, negative potential is more, positive potential is less. So negative potential dominates. So at all these points, the resultant potential is minus. So with respect to y-axis, at all the points on this, positive. At all the points on this, negative. At all the points on the y-axis, the potential is 0. So as you move from right side of the dipole to the left side of the dipole, so positive value, the potential is positive. On the y-axis it is 0. On the left side it is negative. Potential changes from positive to 0 to negative. That way it is varying. Potential varies inversely. It is inverse square law. Suppose if you on this it is 0. Potential changes like this. So this way, electric potential due to a dipole for at all the various points. In the first quadrant it is positive. In the fourth quadrant it is positive. In the second and third it is negative. On the y-axis it is 0. On the positive x-axis it is plus. On the negative x-axis it is plus. So suppose if he is asking to find the potential difference between A and C, at A it is plus V. At C it is minus V. Total difference 2V. Plus V minus of minus. So that is plus. So it is 2 times the potential. So these are the points you have to make a note. Very important. So potential difference. Suppose if he is asking to find the potential difference between point A and C. So delta VAC is potential at A minus potential at C. Potential at A it is plus V. Potential at C it is minus V. It is 2V. More potential difference. That this you have to remember. Okay. Next, similarly, potential at any point on the dipole, for a short dipole, 4 pi epsilon naught, it is P by R square. This is the potential. And this potential is directly proportional to P, inversely proportional to R square. It is varying inverse square law. Potential due to this varies inverse square law. So V1 by V2 is P1 by P2 into R2 square by R1 square. This you have to remember. You know, potential due to a point charge is 1 by 4 pi epsilon naught Q by R. It is inversely proportional to R for a point charge, but for a dipole it is inverse square. Very important point to know, right? Thank you.